actual exam, you'll note that I'll have these as well, right? So even if you have your cheat sheet, you're going to have these things on the actual exam, right? So here are a bunch of stuff that you could use for this. So with regards to the practice exam, though, right? I'll put these in. Just remember that any math that's on the exam isn't hard. Don't leave questions blank because there's no partial credit I can give for them. If your answer is like exceptionally clever, I can give you extra credit points for that too. There's also 5 points baked into the exam of basically a pre-curve / extra credit. So that just helps with keeping this. I found that helps with keeping the scores where I want them to be. So the first page is fairly straightforward, and it's going to be the same as on the actual exam, which is here are the nodes A, B, C, D, doubly linked list. For each of the following questions, please indicate which node is being referenced by the chain of variables. So D.previous.previous.next. .previous, that should be B, right? C.next.previous.previous is B, and then B, let's see, if we do .next, and .previous, those cancel out. .next.previous, .next.previous, that's also B. Yes, I am the type of instructor who will make all the answers the same on a page, just so that I can make it easy for me to grade. This is exceptionally cruel to this poor freshman who are very full of self-doubt, but I don't go for the multiple choice as much on these exams. All right, so these questions over here, write the sequence of commands that will remove a tail from a doubly linked list, and then draw it. The important thing that for this page is the drawing what happens. Sorry?
You should put that question first.
What's that? Oh, well, the reason being on the actual exam, you're going to have a question that says, here's a bunch of commands. Please draw what happens to a linked list of size X after these commands run, right? So here, write the commands that will remove the tail of a doubly linked list. So for a doubly linked list, that would basically mean we have to disconnect the tail from the one in front of it. So we would say what? Tail, let's go ahead and write it out because otherwise that's insanity. So tail is equal to tail.previous to move it backwards. Then, so we've got that, and then tail.next is equal to null, so that it no longer points to the old tail. And that's all that needs to happen to remove the tail. Right, it's fairly simple if it's a doubly linked list. Using a linked list with 3 nodes, draw what happens as each line executes when you remove the tail. So over here, I would draw basically that we would go from this node. Let's see. So I don't want to spend too much time drawing because that's not the important part for this. Right, there's much more point-worthy stuff here. Right, but I'd note that this guy goes from the tail. Then, right, this is the tail. Oh, sorry. I can do this. This is the tail. That's the tail. And then this points to nothing. That's kind of what I would draw. Or I could just simply draw that. As long as you're just showing what happens when you're going on, when it's going on. Write a sequence of commands that will add a new item to the index 0 of a doubly linked list. That's just sorry. Sorry, sorry. You'll see me yawning a lot. My toddler decided it would be a perfect time to get a fever at 8 o'clock last night. So, yeah, well, after we went to shul and everything too. So, we managed to. So he came home and my wife, he's sitting on the couch with my wife, and I was like, does he feel a bit warm to you? And I'm like, of course he's going to feel warm to me. And I'm like, yeah, he's running in pretty high fever, so we're getting it under control. Decided to maybe throw up in his bed this morning, and then that was at 6 o'clock in the morning, and then I went back to sleep after that and woke up at 7 to cover a lab. So yeah, tired. All right, using a linked list with 3 nodes, draw what happens as each of those lines executes. So just simply, as long as you're expressive and it's correct. Yes?
I just have 2 quick questions. For the actual coding, do we not need the if statements?
No, because you're working on a specific clause.
Okay.
So I only just care about that clause.
But we need to instantiate that node number 6.
I mean, ideally, yes, but yeah, it would be best if you instantiated that. But again, ideally, you're going to be just simply drawing code. Yes?
And also, do nodes 1 and 3 connect as well?
Nodes 1 and 3 in this one or this one?
I guess 5.
In question 5, no, because it's not circular. All right. So once you do the drawing questions, you'll have 2 questions about dealing with lists. You can view them as either lists, or I'm going to assume that you're viewing them as array lists. Suppose you have some list of integers. Write a method that finds the minimum and maximum values stored in the lists and return their sum. Right? And you'll note that I have this handy dandy return statement already written for you. So there's the function exam.java, just so that we can get syntax highlighting in. I'm using a text editor just because that's a good analog to to the limitations you're going to have. Okay, return min plus max. Right here, we're just trying to find the smallest number and the largest number in a list of integers. So what we do, so we can use a for each loop over here. So for each int val in list, right? You could use a for loop as well, a regular for loop, but it doesn't really, again, we don't really care too much about which one we use. If val is greater than the maximum value we've seen so far, then, so if val is bigger than the biggest value we've seen, then congratulations, it's the new biggest. And if it is smaller, let's go ahead and shift this down. And if val is smaller than the smallest value we've seen so far, then it also is the smallest value. And you could do that as 2 separate for loops if you wanted, but I find it quicker to do it as 1 for loop like that. So that's all you need to do, just simply iterate through it and use that. Or we can just simply say, or we could be int I is equal to 0, and I is less than list.size, important there, I plus plus. And then if, so one of the ways that you can almost one of the things that I can look at and basically go, yeah, this student's going to fail the exam, is that if we're working with lists and you decide to do this and use the array notation, because that will mean that you really haven't done the homework or you've been getting it from someone else, because that's not the way lists work. You get a huge error if you do that. And I will penalize that, but it's generally I don't really need to penalize it so severely because the rest of the exam takes care of that. But it will get pretty heavily penalized. So you use the get. So if list.getIndexI is greater than max, right? Both the way I did it before and this way are completely valid, by the way. They're both going using the for each loop or using this, right? Just remember, use get I. You can't use the array notation here. So what is the big O runtime for this? What's the time complexity? Now, again, I'm just going to assume, because it's an exam, that you're going to be assuming that this is an array list. Okay? If this is an array list, how long is this going to take? It's going to take, well, we go through each of the n items exactly once. Get operations take O of n, take constant time. So we've got n constant time operations that's going on here. So this takes O of n time. However, if this was a linked list, you might ask, what time would this take? What time would this algorithm take if it was a linked list? O of n squared, because each of these get operations in a linked list is O of n time. And we've got n of those operations. Okay? But as the final aside I have to this, what if I switch it back to the for each loop? How long does this take for an array list? O of n time. How long does it take for a linked list? It takes O of n. Now the reason it takes O of n for a linked list is that it uses the iterator, which keeps track of where it is and just progresses to the next item. That's what the iterator does, right? I haven't really talked about what the iterator does too much, but that's the entire point of having an iterator, is so you don't have to keep using get to go through something. So ideally, you can just simply put in O of n, right? Because I'm going to assume it's an array list. But just I'd be aware that basically a good extra credit opportunity might be considering, hey, my code will run differently if I'm using a linked list or array list, right? So if you feel confident in that, that would be a good thing. Remember, all questions are essay questions, even the ones that have a small little space, and you could simply say, hey, it's this for a linked list, but for an array list, it's this. Good extra credit opportunity there if you're feeling comfortable. All right. Suppose you have some list of strings. Write a method, reverse words, that returns a new list with all the strings reversed, right? So here we've got hello, world, nice, and it turns into Ole, Dwal, and Ecken, or Essen. Now the thing here is, remember, we're not turning it into hello, world, nice to nice, world, hello, right? We're actually reversing the inner contents of the list. And we are returning a new list as well. Right? So now I like this one because there's a couple of pitfalls in this one. A first pitfall is the very first line, which is, let's go ahead and do list of string output is equal to new list. All right, I've already made a mistake. What was the mistake I made? Well, yes, that's the solution, but what is the mistake I made? Yep, I can't create a new list object over here. If you do that on the exam, that's going to be like a point mistake because, again, it's one of those things that I can't differentiate between you just being pressed for time on the exam and just simply forgetting it versus you not understanding the whole thing. And I would obviously, on exams, I always like to, some places I give in favor of the student, but this is one of those things you just need to remember. So here we want to say list output is equal to new array list. And then we'll return our output at the end. So what we have to do now is we have to go through all the items in the list for string word in list. All right, for every word in the list, what do we need to do? We need to reverse the word, and then we need to add it. So if you want, you can create your own function. You can always make more functions if you need to. But over here, I'll just simply go and write this in here. So for every word in the list, reversed is equal to blank. And then you have to use and then there's not, just with string, there's not an easy way to reverse it. If you use a string builder or something like that, there's actually an easy function in that, which I'll show in a second. But over here, but using what we have taught, there's not really an easy way to do it. In Python, it's super easy because Python is like that. But for let's see, for C, we can't use the iterator over here. So for int I is equal to word dot length with parentheses. Again, it's one of those weird things about Python. Oh, it's I minus 1, right? Last index is I minus 1. And while I is greater than or equal to 0, I minus minus, right? Just simply iterate backwards over it, and then say reversed plus equals car word dot car at I, and then output dot add reversed. It's a bit more complicated than I would like for an actual exam, I feel. And then again we return it. If we use a string builder instead, we could just simply say, which is basically what a string builder is the entire idea here is that strings are expensive, or string concatenation is expensive. So let me just simply just refresh myself, because again I'm jumping between two programming languages all the time now. String builder B is equal to new string builder, right? This is how you create a string builder object, just like that. B dot, what is it, add, hello? Not add, was it append? That's what I thought. Can never remember if it's add or append. Okay, and now you can use a function, I think reverse, which will do it. So string builder is kind of amazing like that. So string builder B is equal to new string builder. And then we can just simply say that we want B dot append word, and then B dot reverse, which returns whatever has been appended into it reversed. Both of those ways are perfectly fine, right? The entire point of me using this string builder, which most of you have never seen before, right? You've seen it because you work with Java a lot, right? But if you've basically come across something in your various internet searches, right, looking for how to do something easy, like how do I reverse a string easy, and you find this is the way. As long as it's valid in Java, it's free game. It's fair game. You can do if it's valid in Java, you can use it. There is no need to be limited. The only things I do limit you on is basically when I say in the program, don't use this method or don't use this. Like later on, I will have something that says, oh, like in the second exam, I'll say do this, but you can't use the size method, right? Something like that. So, but that's for the second exam, not this exam, right? But like, so obviously, but otherwise everything is fair game. So, again, how long does this take? If we are n is the number of strings, again, for either case, because we're using an iterator, it will be O of n time. Okay.
Wouldn't the first one be O n squared?
What, this?
No, I mean the one with the for loop inside where you have.
The for, if it's a, for, oh yeah. If for the way I had it, so I'm saying for either case, for a linked list or array list, let me be explicit here. For a linked list or array list, this will run in O of n time. For what we had earlier, now this will still be O of n time, because we're not using a get method or a set method, right? If I used the index, it would take O of n squared.
But there's two for loops there.
But that goes over each character in the for loop. each character in each for loop. Here I'm saying if, I prepended this by saying if n is the number of strings. Now if it was the number of characters, in either case it would be O of n squared, right? It always depends on what n is. Here I'm saying n is the number of strings, number of items, and we can assume, since we're looking at the number of strings, that we can have the baked-in assumption that basically each string is going to be roughly of equal number of characters. Right? That basically each string in there is going to have roughly the same amount of data. It's a silly assumption, but not necessary. It's not like the silliest assumption we'd ever have to make. Most of these questions will be worth 10 points. There'll be 2 of these questions. They'll probably be worth like 10 points or something. Plus the 2 extra points down here for the time complexity. All right, so this is a linked list. It's composed of generic nodes, has a head, has a tail, has a size method, and they're doubly linked. On the exam, pretty much everything you're going to be dealing with is singly linked. I use doubly linked for the practice exam because that involves more writing. So write a method called delete list, which removes all the items in the list, making it empty. So instance method inside linked list. So to delete everything in a list, it's actually fairly straightforward. Okay, and you can do it in constant time, which is kind of amazing. The most efficient way to do it is to say head is equal to null and tail is equal to null. And then one more thing just to remember, size is equal to 0. Just to make sure that basically so head and tail will get garbage collected. Yeah, so here, this will garbage collect the head and the tail, which will make the next things in the list also get garbage collected, which will make the next things in the list get garbage collected, and kind of just eat it. Yeah.
So since it's a doubly linked list, though, wouldn't there, like, head.next.previous be pointing to head, so there's still a pointer going to it?
Wouldn't that be collected when it's done with that function call?
Let's see.
There's still pointers going to both
There's still pointers going to head and tail. Interesting.
That's the same. That's when you do an insert in the wrong order and you lose the pointer in the opposite.
Oh yeah, but for a doubly linked list and a singly linked list, it does work a bit differently. He's saying that basically, yeah, we got a null right over here, but the state is something like this. Or head is equal to null, but the state is still this. And there's still something pointing to this. So technically the question is, does that keep it alive or not? That's an excellent question, and actually one that I'm not really sure about the answer to. So let's assume that that won't work. And instead, what do we need to do? In that case, what we need to do is simply go while we'll have to do this with current. So node e current. I was assuming that would work, but you may bring up an excellent argument.
It's like you said something. Sure.
While current dot next, so see current is equal to head, while current dot next is not equal to null. So while there's still something next behind me, let's see. Let's just simply have a next node as well. Next is equal to current dot next, so that we store that, and then we need to say that current dot prev equals null, current dot next is equal to null. So completely detach this guy, and then say current is equal to next. And then when we're all, and then at this end, still want to say size is equal to 0. We could do like size minus minus as we go through this, but that'll be more explicit. If you had to be explicit, I'd make it worth way more than 3 points. The main thing is just remembering to set that size to 0. Count. Write an instance method called count. Count.
What if you do that and you didn't disconnect the
And didn't what?
It wouldn't let you? You just said size is 0.
Oh, what if you said size of 0? That wouldn't remove anything. That would just really mess up a lot of the add and remove operations. So write an instance method called count. Count iterated over a linked list and returns the number of time an item occurs in the linked list. So this is an instance method, so you can access head, tail, and the node class, right? So it's inside a linked list class is kind of the big thing here. So let's go ahead and use it. So again, we're going to do the whole node e current is equal to head, while current dot next is not equal to null, while there's still stuff after me. This will work for both the linked list and both the doubly and singly linked list. We'll need a counter. Int counter is equal to 0, and at the end we're going to have to return that counter. And what we have to do now is basically we want to count that item. So what we say is for one mistake, that a common mistake here is saying if current equals item, or saying current dot equals item. Now the issue of what's going on here, while your logic is correct, your syntax is not. Logically, you're thinking, hey, what you're forgetting here though is that if you do that, current is a node, item is the thing that's stored in the node. So what you need to do is do current dot item dot equals item, or current dot data dot equals item, or I don't really care what that is so long as you understand that it's the thing inside of it. So basically, if it's one of those items, congrats. We say we go counter plus plus, right? And then otherwise we say current is equal to current dot next. Move the counter up one. Yeah.
Why do you use the dot equals method instead of the double equals method?
So the double equals method would compare, does this item and the other item have the same memory locations? Not if they're the same, not if they have the same information in them.
So what if the item is an integer? Do integers have the dot equals?
Integers do have the dot equals, but you can use the double equals.
Okay.
Using the dot equals and using double equals for me is again a 1 point minor mistake, because again it doesn't show me that you don't understand the problem. It shows to me this would create a bug in the program, but not in your logic, right? Again, what I'm primarily looking for is your problem solving ability and the ability to manipulate stuff. If on the other hand you said something along the lines of current.next is equal to current, then we have a problem. Because that would not move anything, that would be an infinite loop, and you'd also be destroying the linked list in some way, shape, or form. Right. Write a static method that takes in two sorted linked lists of integers and merges them into one sorted linked list and returns them. So this is the first of many problems that deal with sorted linked lists. Since it's a static method, you cannot access the nodes. In other words, no head, no tail, no next, no previous pointers. This means that you have to use the add and removes. Previous one. What was the time complexity? O of n, because we're touching each node once. Here with merge, we're allowed to remove the items from A and B, but otherwise you cannot access the node. You can't basically. We can't use the .next, we cannot use .previous, we can't use head, and we can't use tail. So this is something that you would solve much like the cryptography problem in homework. And we're going to create a new linked list out here. I also made it integers just to make it easy to sort. So let's go ahead and do linked list integer. And you don't have to use generics on the exam, right? That's perfectly okay. I'm not going to count it points either way because not using generics will just give you warnings and stuff, but I like to use it because it's good practice. List, or rather, I'll call it out, is equal to new linked list. Okay. Next, we've got list A and list B, and they both need to be sorted. Now, there's no need to write something like bubble sort. If we did that, that would be actually very horribly inefficient because bubble sort relies off a lot of get and set methods, which are super expensive for this kind of operation. So instead, we're actually writing the merge step of an algorithm called merge sort, and it's actually possible to do this part in O of n time. And what we're saying is that basically, if you think about it for a second, if we've got a list like this, so let's go ahead and make two fake lists over here. So we've got 1, 3, 13, 17, and we've got 2, 7, 8, 9, 12, 5,000, right? Reasons for that, well, 5,000 and 20,000, right? Again, the caveat here was that everything is sorted, okay? Didn't say they have to be the same size or anything, too. So, however, our output needs to basically merge these guys. Now, if we look at this, at the first items in this, 1 is less than 2, and 1 obviously should be first, right? 1 is the smallest item. But if we also know 1 is smaller than 2, then because everything in this list is sorted, we also know that 1 is less than 7, 1 is less than 8, 9, 12, 5,000, and 20,000, right? Or rather, if we know that the head of one of the linked lists is smaller than the head of the other linked list, we know it's smaller than all the items that remain in the linked list, right? Similarly, if it was like this, 2 we would know is smaller than all the items over here, so we don't need to check them all. So really, we just need to compare the heads against each other. So what our algorithm is going to be is while list A dot size is greater than 0 and list B dot size is greater than 0. So long as those are both greater than 0, right? So long as one of them still has an item in there, then what we're going to do is that we're going to compare the heads. If list A dot get 0 is greater than list B, or sorry, let's go with less than list B dot get 0. So if A is the smaller number, list A is the smaller number, what we're going to do is we're going to do out dot add. We're going to add to out list A dot remove 0. So what that would do is that it would remove 1 from consideration over here, right, and add it to our output. The else is and there's an else condition, but it's fairly straightforward. Else out dot add list B. If list A's head is not smaller, then list B's head must be smaller. And yes, it's possible for two things to be equal, but honestly, don't really care because this will catch one of them.
Is null always less than everything else?
So we're not going to get a null or anything like this.
When you start comparing, list B, get, and it'll be nothing.
Well, the
something.
while over here, it's going to stop one of the ones.
Oh, I thought you had to.
Yeah. So when one of these lists is empty, so eventually one of these lists is going to empty out, right? And we'll go through and it'll empty out these things, right? Notice that 5,000 and 20,000 are the biggest items here. That's what's left over. So one item's empty, so we're going to stop here. So we still have 2 items here to add out. Now, what we're going to do is be actually extremely lazy about adding the remaining items in. They just need to be added to the end of out. So what we're going to do is we're going to say, and because we don't know coming out of this loop without checking which one of these still has items in it. So we're just going to assume both of them have items in it, and simply copy paste the same loop. While list A dot size is greater than 0, out dot add list A dot remove 0. A fairly short statement to do there, right? You might break it up into multiple statements too. But what we're saying is that, okay, we got to the end, one of these 2 still has items in it. If A has items in it, we're going to keep removing the first item and adding it to the end. Obviously in this condition, this won't run. Then we just simply do same for list B, and this is perfectly fine to do on the exam, basically, if you have to do some boilerplating code like that. You can just simply say, for me, you can comment and say, same for list B, right? Because it's literally just copy pasting this bit of code, but you're replacing list A with list B, right? So that's okay for me, right? It's okay for you to write that, especially if you want to come back to it possibly later. Then just remember to return the output, and that will return the merged. Now, I bet you I'm asking how long did that take? The time complexity of this algorithm is because we are dealing with just adding to since we're just sizes. This size operation takes constant time. List.get. List.get 0. These are all get 0 operations, so those are constant time operations, even though we're dealing with a linked list, because getting the head or tail is constant time. Removing the head is constant time. Adding to the tail, constant time. So the question is, how many items did we go over? Well, there's 2 answers. The first answer, which is the one I'll give you full credit for, is if you say it takes O of n time because there's n items, right? N items total between list A and list B. The extra credits answer is if you read the book, and they have a bit on like what if you have 2 lists that are vastly different sizes. In that case, it would be n plus m, right? Because there's this could be 10 items and this could be 1,000,000 items, right? Technically, that's the more correct answer, but here we're making because we're in data structures, we're just kind of making the simpler assumption that these 2 lists are roughly equal in size. So the most correct answer is n plus m, right? But saying list n will give you it works full credit for my exam. All right, so this one I need to remember how to do. Haven't done this in a while. Write a method that reverses a doubly linked list. The method will be a instance method for linked list, so you can use the head and tail method and refer to linked list using this keyword.
I got a question about this one.
Yeah.
I know it's an instance method, but will we be allowed to use a remove, like without coding the remove method?
Yep, you could use add and remove, just like that. So that is one way to do that. So that is actually an excellent solution, but then we're going to try it with playing around with pointers, okay? So always when you're looking at these problems, kind of see if there's a way you can use add and remove to your advantage. Now, when you're dealing with a method like this one, where I say, hey, you're creating a new add method or something like that, or creating a new remove method, obviously, in this case, you're making an add method that's different, so I don't want you to use the add method. Right. But here, this is perfectly fine. So the idea here is, let's see. What would you do in that case? We could just simply create a new linked list, right? Linked list temp is equal to eTemp is equal to new linked list. Again, I'm going to go for this with as little thinking as I can and do it as simply as possible. For item, while, I'm going to do a while loop here because why not? So while this dot size is equal to 0, is greater than 0. So while there's stuff to remove, I am going to say this dot remove 0 and temp dot add it. So this is just simply going to move everything in the same order from temp to from this linked list to the temporary linked list, right? So now our linked list is empty, which means now we can start doing stuff to it again. So now we'll say, let's see, while temp.size, and I can use it without parentheses here because I'm inside I'm inside a linked list method. So what I'm going to do is I'm going to say remove the head, but add it to index. I'm going to say temp.remove head. So yeah, a lot of changes over there. First, I'm going to say this. We're going to add to our original node at index 0, remove the current head of the temporary linked list. And what that will do is that will add the head first. And then we'll add the item after the head before the head. And it will add the item after the head before the item after the head. Right? So it's going to add them basically by adding each item progressively to the head, it will reverse the linked list. And the head and tail will automatically be adjusted. Honestly, that's the easiest way to do it. What's the runtime of it? Moving, it's O of n. O of n, because we're adding to the head and tail and only working with the head and tail. Doing it by moving the pointers, actually, I'm probably going to skip over because that's a pain. Yeah. But think about how to do it. Think about how to do it. I'm not gonna like, actually, I'm gonna say that like that basically that doing it with a singly linked list or a doubly linked list is actually a pain because it requires a trick, and unless you know the trick, it's really, really tricky. So I would never like tell you flat out, like here is a singly linked list, reverse it. But if I gave you different selections of code and asked you which were to reverse a linked list, that might be fair game, right? So let's go ahead and notice that this one is 15 points as compared to the 10 points. This kind of emphasizes that I consider this important. Right? So again, my way of using points is basically saying me ranking the difficulty of these various questions as well as their importance. Okay, suppose we have a new type of linked list, a sorted linked list. It is a linked list, but it keeps all the items sorted. It is impossible to have an unsorted linked list. So it's impossible for a sorted linked list to look like this: 1, 4, 5, 8, 7. That's impossible. It's never going to get in that configuration. If we add an item, if we add 3 to this linked list, it's automatically going to figure out that it needs to go that the 3 needs to go between the 1 and the 4. I say automatically, but that's the part we have to program, right? So there is no add at a certain index method that we're going to use here. We have to use the pointers essentially. So the key here, though, is that because it's sorted, we can kind of figure out when we need to stop by comparing the values of where we are, where we currently are. Because if the value we're currently at is, if the next value is the one that's large, so if basically what we're looking for if we're adding 3 to this linked list, if you think about it, we're looking for the point where we can insert an item where this value is smaller. The value, let's say if this is current, this value is smaller, but current.next is larger. And once that's in, we can just simply create a new node and insert between them. If we get to the end, then it's bigger than everything else, so we just add it there. Right? So first and foremost, for add, we kind of need 3 conditions here. Or we need to do at least our first condition here. Public void add e item. And so we need a couple of conditions here. Where will this actually be a bit weird? Okay, so I'm going to go ahead and just write basically the first conditions that I can think of before moving on to a generalized case. I always try to figure out what those edge cases are before I move on to a generalized case. We know at most there's going to be 5 edge cases, right? Let me think through them and think if they're relevant here. Okay? First edge case number 1. I'm adding at a bad index. I'm adding out of bounds. That's not going to apply here for once because we don't get to choose the index, right? It's going to choose it automatically. Okay. So what if I'm adding the very first node to a linked list? That seems relevant. We might need it. We might have to erase it later. It's okay to erase. So if size is equal to 0. If the size is equal to 0, then first off, let's go ahead. Since we know we're never out of bounds, we're going to need this node adding is equal to new node item. Okay. If size is equal to 0, then let's see. Head is equal to adding. Let's remember to do size. I'm going to remember to do size plus plus down here, right at the very bottom. So if adding, so I don't forget about it later. So head is equal to adding, and then I'm done, right? Let me take a look. Else if, and really that's essentially the only probably case. But now we know that head exists. What if I'm adding it to the very end? Well, I'm not going to keep track of tail. That wasn't a requirement of this problem, so I'm not going to. Doubly linked, singly linked, I'm going to assume it's singly linked just to make it easy for myself. Okay. So yeah, this is pretty much the only condition I really need, or one of the only conditions we need for right now. I'll need something at the end, basically. Item is larger than largest item, but I'll tackle that case later. I'll actually write the generalized case first, which is, so I'll go ahead and say node, so else node current is equal to head. And if it seems like I'm kind of less sure about this question, it's because I am. I only answer. I've given it this. I wrote this question without knowing what the answer was the first time I gave it. So because I know I can figure it out. But yes.
Do you need to specify the head, the adding up next to head next to adding to the?
So if size is equal to 0, right? So what I'm going. So that's actually an excellent idea, which is let's say. So that's actually an excellent point, though. Else if head, yeah. Else if head dot item is let's see, item is less than head dot item. What if the item I'm adding is the smallest, right? What if we need to add to the head? right? If I need to add to the head, then I need to say head is equal to adding head dot, or rather, right? What's the order I need to connect things? I got to do adding dot next. What would have happened if I had done that? I would have garbage collected everything. So adding dot next is equal to head. Head is equal to adding. So we're good there now, right? And we obviously need this because we need to make sure that the head gets initialized. I mean, we could simplify it and say if item is less than, if size is equal to 0, or item is less than head dot item. But right now, this works out a bit more explicitly. So I think we've got all the cases we need. So otherwise, we set up a node current equal to head. Node e current is equal to head, and we can. And I'm just going to use less than and greater than signs, even though that wouldn't be correct, right? We'd want to be using compare to, but less than and greater than signs make it easier for the exam and for writing the answer. So if the current is equal to the head, then so what we're looking for is while current, we know that, so let's see, current dot item is less than, so while current dot next is equal to 0. I'm sorry, not dot next is equal to 0. Current dot next is not equal to null. While there's still stuff after me, right? I'm not going to try to figure out all the logic in that if statement. I'm just going to look for that place to insert it. Right? If current dot item is less than the item I'm looking at, and item is less than current dot next dot item, which is weird, but basically what I'm saying is, okay, we've got the thing I'm trying to insert, that's item. If its value falls in between, basically in Python I could do this expression, right? That's legal in Python, it's not legal in Java, wish it was. But what we're saying is basically if item is between these two items, then that means that we want to put item in between those two nodes. So in that case, what we would say is adding dot next is equal to current dot next, right? Attached adding to the next node, and then say current dot next is equal to adding attached. Then that attaches the current to adding. So that gets that node in between them, right? We've already created that node up there because we know we can use it. And in that case, we're done. We could just leave that going. Current dot next is current is equal to current dot next, right? We could leave that just going as is, right? But to be explicit about it, we're done. So break or return. That will break you out of that loop. Actually, return would be a bad idea because in that case you wouldn't do size plus plus. Now, if we get to the end of this loop, however, without adding there, let's see. While current is not equal to, current. So now we need to say current is equal to current dot next. So now we have to ask ourselves, so this seems to add everything except, this seems to handle, what case is this missing? Yeah, what if it's the largest item in the list? So how can I properly handle that? Right? There's a couple ways that I can hack this out, but I'm looking for an elegant solution. Right? I could have like a flag over here that said, hey, Boolean added is equal to false, and then set added, and then what I could do over here, if I added, I can say added is equal to true, right? And then say over here, if not added, then add it to the end, right? Does that make sense to everybody? Why I would want that? Yes?
So inside the while loop, once we reach the end of the list, we'd be checking current.next item, which would just be null.
Ah.
Is that right?
While current.next is not equal to null. So current.next is always going to exist. That's part of the reason I checked it like this rather than saying while current is not equal to null, right? Because if current is not right, that's why I always check if current.next is going to be equal to null and then stop there. So
Put it outside the while loop.
so
Let it fall through null at the end.
right, so if current.next is equal to null?
I mean, it has to be.
Yep.
null at the end, so
If current.next equals to null, yep, that's probably the most, this is probably actually the best way to do it. So we go through the while loop. We're done with the while loop. If current.next is null, that means we made it to the end of the while loop without adding the item. So then we would say current.next is equal to adding. And that would just add that onto the end if it was the largest item.
you need to check this null because it would have broken if it actually.
No, because the break would have broken out of the while loop,
Oh yeah, it would have.
but we'd still be in the if. And again, the safer way to do it, the more explicit way to do it would have been to use this Boolean added and then change this to if added is equal to false. Then we know that current is the last item, and therefore current.next is equal adding is the next item you have to run. So that is the, again, most complicated question on the exam, I think, by far. And again, it was a matter of just making sure that our assumptions were written out first, right? Okay, what if it's the only thing in the list? What if it's it's less than everything else? What if it's greater than everything else? How do we handle that? I mean, and if we were keeping track of the tail, we could have handled that another way. So this was the add method for a sorted linked list, and I seem to be putting a lot of sorted linked list related questions on there. So, so that should give you like kind of a hint, hopefully, about what I care about. Okay, so analysis. 20-point question, also going to be on the exam. So you know for a fact, basically, that 20 of the points are going to be the analysis. About 20 to 20, let's say, and about 20-ish points are going to be the lists. These list coding questions. So 20 points there, 20 points there. They're going to be similar in difficulty. Sorry, they're going to be less difficult than the homework questions, essentially. And then about 10 points for these other questions. So that's about 50 points you know. 50 points between pointer tracing, drawing the lists, and the analysis, which leaves about 50 points-ish, about 50-ish points left for linked lists, right? 50-ish, because of course I'm not counting the big O time, because you're also going to have about 10 points worth of big O questions in there, right? Those 2 point. And the only big O questions, again, are going to be at the end, which say, this is what it's going to do. Oh, and I said the solution must run in O of n time, so our solution did run in O of n time because we went through each. That just simply means we need to hit each node basically once or twice or 3 times or something like that. But we don't hit each node n times. All right, so a list can be implemented in a number of ways. Compare and contrast an array list and a linked list. In what situations would you use one would implement a list over another? Okay, so as I've mentioned, there are basically 3 ways that the 3 big ways that linked lists and array lists differ. First, it is memory usage. It is the modifying the list, in other words, adding and removing. And then it is getting and setting, which are retrieving values from the list, or replacing, retrieving and replacing. So let's talk about memory usage first, right? How do array lists use memory? They use memory by having an array of pointers. And when it fills up, what do? You double the size, which means that on the one hand, if you know exactly how big it's going to be, it's efficient. In fact, but once we double the size, it becomes potentially possible to waste space, right? You can waste space with an array list by, allocating pretty much twice as much if you need, if you're unlucky. Like my classic example is if my capacity is 1 million and I've already added 1 million items, so now I've added my 1 million and first item, I'm going to double my capacity to 2 million, which means now I have wasted, and that 1 millionth item is the last one I'm going to add. And that means I'm going to be missing, that means I'm also going to be basically not using 999,999 points, 32 bits worth of memory, or 4-byte pointers. So that's how it could waste memory. You could waste memory also by potentially removing items, right? I add 1 million items and then I remove half of them, and now I'm wasting 500,000 slots. Okay, that's another way we can waste space like that. It's not as common. However, one thing that if you really wanted to go for extra credit on this one is to mention that there is a method that exists in ArrayList that actually will modify the capacity down to what the current size is. Yep, it's that one. So if you use that, you can actually be a bit more efficient with memory like that. However, once you use that method, right, it takes O of n time to basically shrink the capacity down, because how are you shrinking the capacity down? Well, you're making a new array list exactly the same size as the size, and therefore copying over, which takes O of n time. So it does have a bit of more of a memory cost. But if memory is what you're concerned about, that's a fantastic way to do it. Okay? On the other hand, linked lists don't have that issue where you have to trim it down to size or expand. Linked lists instead use extra memory in overhead, right? Every single item you're storing requires both a node to store it in and a pointer to the next node, and possibly a pointer to the previous node, which is basically anywhere between 8 to 12 bytes. So if you had an array list that was basically shrunk down to the appropriate size versus a linked list, the linked list is going to be less memory efficient because it's got those extra overhead, right? The linked list the array list just has references to the items being stored. Linked lists, on the other hand, they have to store both the pointer to the items, so the same as array lists, as well as the next pointer and the previous pointer. So possibly 100% or 200% more overhead, so to speak. That's not to say that that's bad. That's just simply the trade-off you're looking at. If you're not careful with array lists, you're going to waste space, which is like even more of a mortal sin. But is space expensive as when compared to time? No, it is not. Space is cheap. You can always buy more. I can literally go on to Amazon and ask for more space, and they will ship it to me in a nice box. And by nice I mean cardboard. Okay, so the next thing is the modification, right? I think actually I have this written out. Practice exam solution. Yep. So the big thing for the add and remove is, in general, takes O of n time to add or remove something from an array list. Array list is O of n time in general. Okay? Because this is always if you add or remove, if you add it to the front or remove something to the front, you have to shift n items over. If it's somewhere in the middle, on average, n over 2 items. If you're adding or removing to the end, removing is always going to be constant time if you're removing from the end. If you're adding to the end, probably going to be constant time, except in the case where you have to reallocate, in which case it's O of n time again. So that's the thing about array list. It's O of n except for adding to the end, except if you need to reallocate, right? Now for the answers, to get full credit for these, you will need to use big O times, right? If you don't use big O times, the only other way you're going to get full credit is to say linear time versus constant time, right? If you don't explicitly put in big O, then you have to say, then you actually have to like mention if you mention basically linear time, or you have to move n items, so you don't necessarily have to like use big O. If you say n or n over 2, but you can't say just fast, slow, right? That's what I'm trying to say. Or array list is better. So compare and contrast. You got to give me a reason. Because also they're not necessarily better. With memory usage, right? We explained that they're actually what's better depends on the certain scenario. For a linked list, if you're adding to or removing from a location you have a reference to, head or tail, then it's constant time. If you know if you have a pointer to where you're adding, you just simply are adjusting pointers. And that's fantastic. In Java, they're called references, but I'm calling them pointers because, honestly, that's less syllables. So it takes constant time. On the other hand, anywhere else, you need to search for that location, and it'll take O of n time. However, what's interesting about linked lists, is that if you save that location somehow, that middle location, and you want to add a million items to the middle, then it's just O of n time to search for the first item, and then you can add all the items in there however you want. Linked lists are fantastic if you want to like split it up, if you want to section it off. Like we saw that basically it's very easy to split an array list, a linked list, and to basically concatenate array lists with one another. So that's pretty cool. Like to add all the items from an array list to to add two, if we've got an n over 2 size array list. So if we've got two array lists, each n over 2 size, right? So combined total of n items. If we were to add them together into one single array list, or we want to add all the items from the second array list to the first one, so that they all now live in the first one, that's going to take O of n time, or O of n time. If we're doing that for linked lists, it's just a matter of adjusting the pointers, right? To have the tail of the old linked list point to the head of the new linked list, and make the head of and basically just remove the head and tail of the other one, or head of the other one. And it's a constant time operation. You're just moving pointers and saying what's move the head and tail. So linked lists are really good at that. Array lists actually aren't that great for adding things to it. However, where they really shine is this retrieval thing, right? Constant time, get set, no exceptions, right? I want something at a specific index. It will get me that thing at that specific index. No questions asked. Constant time. Linked list, you have to search for that specific index again, unless, of course, you're looking at the head or tail, in which case it's constant time, which barely bears worth mentioning. And we see that we use that a lot with linked lists, but we use that because we're limited to how we can manipulate linked lists. So at the end of the actual exam, let me go ahead and stop the recording for a second.